Yeah, so I don't have anything particular to cover. So if you have any thing to discuss, I can. So are there any questions which solutions are not clear to you? You want me to explain some part? The epsilon gradient. The question on epsilon gradient. It's a tutorial. Very nice. Yeah, so what is the doubt you have? Is there any particular thing? Like, did you look at the solution? No? To see this one, no? So this is just if you have and if you have some number of samples, we are just using Hopking inequality here. So if you have some n number of samples from a particular arm, so what does Hopking inequality tell us? Right? Hopking inequality will tell you that the probability that mu bar belongs to mu minus epsilon to mu plus epsilon with probability greater than or equal to 1 minus 2 e power minus 2 epsilon square n, right? This we know, right? If you have n samples, this is what we know. Hmm. So I think we just choose this probability. Like if I choose, like you just substitute this as substitute this as epsilon, what will we get? And this is greater than or equal to 1 minus 2 into h power minus 2 into ln t by n into n, right? So this n and n gets cancelled. And what else will be there? So this, so this is like roughly like 1 by t, right? That is 1 minus roughly like 2 by t. So with some high confidence, your mean, sample mean will be uh, close to the true mean. So this is the same analysis which we did in explore first then commit algorithm or UCB kind of stuff. If you have n samples, you can see that like, the sample average, like the true mean will be less than or equal to, right? Like the true mean, if you know that mu bar plus mu is less than or equal to mu bar plus epsilon, right? Your mu is less than or equal to mu bar plus epsilon with high probability, which is roughly like 1 minus 2 by t kind of a probability. That's all we are saying. Question in the same thing. Okay. So this anything else in this part of the question? So this after this confidence interval, you find. So this probability, some good term of the probability. This is true. Yeah. So because we want to, we are just doing that. This is about value for this. Hmm. No, we want to outperform this. So we are taking the maximum for this so that we get the output number. And, and after that, it's fine, right? Okay. Yeah. So you are asking what? Fourth question. This like this part, this one, or the second question for D part or the fourth question? Okay. Like the intuition based things. Okay. Okay. So the first one is okay. 4A is okay, or should I explain this? 4A should I explain? Okay. So 4A everyone knows, sir. 4A is fine for everyone. Like the 4A question is if you do greedily instead of epsilon greedy or UCP, whether can we get linear regret, like sublinear regret. I just gave one counter example. Okay, so what is 4B? 4B, we are saying that whenever the time is a power of 2, we'll play the first term. Whenever the time is a power of 3, we'll play the second arm. Right? That was the question, right? And remaining times we play whichever arm has the highest sample average. Right? In these slots, we are playing arm 1. In these slots, we are playing arm 2. Uh, Deterministically. In other time slots, we are just picking the arm which has the highest sample average so far. Okay. So at some time t, if you look at some time t, how many times arm one would have been played for sure? This is the this is not an actual proof. This is just an intuitive because it's I'm not giving a lower bound here as such, but intuitively you'll just get a feel of why this is not going to give you a sublinear regret. So because we are playing arm one at powers of two, right? So during that is like exploration, right? A1 and A2 are exploration. Like those times we are doing exploration. Remaining times we are doing exploitation. So arm1 till time t would have played roughly till log t base 2, right? Because we are playing only in powers of 2 times. And arm2 would have played log t base 3. And so if you assume like even due to exploration, the total number of rounds, the total number of times you would have played arm 1 and arm 2 will be log capital T base 2 and capital T base 3 due to the exploration. Like due to exploitation, we could have played some other times, more times, but due to exploration, this is what we can play, right? Because at most, if you have T slots totally, this many times you would have played arm 1 due to exploration because that many numbers only will be there, right, in this set, right? If you're totally T rounds, you'll have log T base 2 entries in this set A1. Here we'll have log T base 3 entries in the set A2. So these are the slots in which we are doing exploration. In the remaining slots, we are doing exploiting. So we don't know which one will play in the other slot. In these slots, it depends on the average. But in these two sets of slots, we are deterministically playing arm 1 and arm 2. Like, you don't recollect the question? Like, the question is, the you play the sample. Okay. So, on this slot, like slot 1, like slot 2, this is determined. Other sounds, like slot 1, slot 2 is slot 2 sample is super, and we'll play whichever arm has the highest sample among those two. Whether this algorithm will give you a sublinear result or not is the question that is being discussed. So, if you get so we know, so now the total is 30 nodes. Total is correct. Probability equal to 5 and not explanation for round two. So roughly at any point of time, the number of exploration rounds for arm 1 will be log t base 2 less than or equal to log t base 2, and for this it will be log t base 3. So the confidence that we have about that particular the if you want confidence like 1 by t probability, if you want to be correct with at least 1 minus 1 by t probability, due to Hawking inequality, we can like if we have samples of particular amount, we can interval with the probability greater than or equal to 1 minus 1 by t. Just now I have seen that, right? So we know this much, but if on an hour, because we know that the exploit step, we know the regret is at most 2 epsilon, uh, right? Because of the previous thing, like mu minus epsilon, like in the exploration then commit algorithm we discussed, right? So if let's say you have some bound for arm 1 and some range for arm 2, right? So if you're playing the wrong arm, that means the sample average of that arm is better than the sample average of the other arm, right? Let's say let's assume mu1 is the let's assume so what I'm saying is if you're playing a wrong arm, you're playing that because the sample average of that arm is better than the sample average of the other arm, right? So you want mu1 bar greater than mu2 bar. Let's say mu2 is the best arm, but when will we play arm 1? We'll play when mu1 bar is greater than mu2 bar. But if mu1 also, like both of these will satisfy this kind of a inequality, right? That mu1 bar belongs to, like we know this, right? Mu1 belongs to mu1 bar minus epsilon to mu1 bar plus epsilon. This we know, and this also we know. Mu2 belongs to mu2 bar minus epsilon to mu2 bar plus epsilon. If you assume this, and if you know this condition, then you should be should be like mu2 minus mu1 should be less than or equal to 2 epsilon. Just by looking at these things, like if this condition is point, these two conditions are also satisfied because of routing inequality. Then to epsilon. So you can just look at it carefully, you'll understand. I think we made the same argument in explore first then commit analysis. I think it's like this, like maybe I'll just explain you if possible one more time. So let's say this is mu1 bar and this is mu2 bar. Mu1 bar, like we are having, so right now mu2 bar is greater than, like you're not able to see green color. Huh? So let's say mu1 bar, mu2 bar are like this, and we are assuming that this is a bad event, right? Like bad thing to do because we are playing suboptimal. Only when we play suboptimal arm, we'll get a regret, right? So that means what should have been mu1 would have been greater than uh, like mu1 would have been less than mu2, right? Then only this is a bad, right? So we'll have what? We'll have something for mu1 and something for mu2. Mm, only there should be the positive mu2 greater than mu one, right? Then only it's a bad arm. So when is that possible? Like this difference should be less than 2 epsilon. Like I am not writing it carefully, I think, but you can just make some argument like this, you'll understand. Okay, just write it properly that you cannot, your sample average cannot be more than plus or minus epsilon of your true arm. If you want this to be happening, then we can say that the actual difference between the true means will be less than 2 epsilon. You can make that argument by just using these three. Okay. Maybe I should just do this one. So, like, maybe I can just try to explain. So, if if this is human, so when will mu1 bar? What is the best that mu2 bar can have? Oh, like mu1 bar is actually mu1 is actually so mu2 is actually the optimal arm. So, but somehow we ended up seeing this that mu1 bar is greater than mu2 bar. So, what is the worst thing that could happen for mu2? That will be this, right? Mu2 minus epsilon. Like, what is the least value that mu2 bar can take? Mu2 minus epsilon. What is the best value that mu1 can take? Mu1 plus epsilon, right? Yes, and so there is at most 2 epsilon difference between them. If there is, if this overlap, if there is no overlap, then we can never have mu1 bar greater than mu2 bar, right? If there is no overlap, mu1 bar will be here, mu2 bar will be somewhere here. So there won't be any wrong prediction. If there has to be wrong prediction, there should be overlap. If there is overlap, right? Is this clear? If there should be overlap, or if there is no overlap, then this condition cannot happen. If there has to be overlap. Okay. So, so that's why at any given point of time, the regret will be what? 2 epsilon into capital T roughly, like because they are roughly having, this is not a rigorous proof, this is just a vague argument. Yeah, part three is the following algorithm, right? What is, I think part three is you play if the best term, I think we know the epsilon, right? We know that the difference between them is epsilon, like mu1 minus mu2 equal to epsilon, we know. And the algorithm that we are doing is whenever the uh, is this the rule? Like, can someone read the question and tell confirm me if this is the rule we are doing? Hmm. Hmm. Okay. Okay. Okay, so this is the algorithm, right? Like we have the two means of the we don't know which one has which, but we know that the answer is different. So we don't know term has which mean, but we know that the range belongs to these two numbers. Whether the first term has mu or mu minus epsilon, we don't know. We just know these are the two numbers true means, but we don't know whether the first term has what, the second term has what. And what we are doing is for the time is the best example. Then we are playing the arm with the highest sample average. Otherwise, we are pulling both arms once. Okay. Hmm. So this is easy to show that we'll have sublinear regret. So no, subsequently, like you can think like you are deciding that next two rounds you are going to pull one after other. Right? You're doing it in phases. Let's say in some phase you'll pull only one arm. In some phases you'll pull two arms, like two rounds. Yeah, we'll do exploration for each arm once. So let's say in the beginning you don't have this condition. Two, let's say start with mu bar equal to zero for all the arms. Then you pull first arm, you pull the arm, second two rounds will go. Then you'll see in the third round you'll see what to do. So you have to count them as two rounds. So what is the issue? So, so if we have if like one of the arm has mu minus epsilon, the other arm has mu, right? So how many samples will we need to have the epsilon to be less than like the you want, you want that much confidence interval. Okay. So how many samples will we need with some probability 1 by t, let's say. You want to say that with probability at least greater than or equal to 1 minus 1 by t, you want the confidence interval to be less than epsilon by 2. Like by using Hopding, we know how to do this, right? Like if both the confidence intervals are less than epsilon by 2, then this is like one of them is mu, right? The other one is mu minus epsilon. If, if the confidence is less than epsilon by 2, right? If this is less than epsilon by 2, then there won't be any overlap, right? So the best term average, sample average will be greater than mu minus epsilon by 2. The bad arms average will be less than mu minus epsilon by 2. This is mu minus epsilon by 2, let's say. Correct? If the confidence interval, then this will be correct, right? And let's say you want this with probability greater than or equal to 1 minus 1 by t. How many samples do you need by using Hopding? So all that you want is the probability that mu bar belongs to. So you want the mu bar to be less than or equal. For the first term, you can apply this, right? The mu bar should be less than or equal to. Uh, if I call this as mu one, what is the probability that mu one bar is less than or equal to mu one plus epsilon by two? If I take mu one as mu minus epsilon, what is mu one plus epsilon by two equal to? Because of this is the boundary, right? Mm, like this is equal to mu plus mu minus epsilon by two, right? This term. This is equal to So what is the probability that mu1 bar is less than or equal to mu1 plus epsilon by 2? What will Hofding give us? 2 into, like not 2, like e power minus 2 epsilon square n, right? If it's based on n samples. So if you want this to be 1 by t, you want this with a high probability, like the error to be low probability. So what will we get n as? This is epsilon by 4, right? Here. Will it? Hmm. So what will n be? N is something like log t, right? Like roughly, it's something roughly like log t. So after n samples with probability at least 1 minus 1 by t, these two arms will be separated. Correct? You need log t samples. Correct? Is this part clear or should I explain it in a little bit more detail? I can do that because there is nothing else. No, this is because you are saying that this is the epsilon by 2 and you are doing epsilon. So the distance between them is epsilon. Now you are asking so if this interval is 2, let's say epsilon is 2. So this interval you want it. So you can assume that there won't be any overlap. If the difference between them is epsilon, like this is totally epsilon. This is totally epsilon. So if you make this, then you got you. So there is only epsilon by 2 on this side possible. There is epsilon by 2 this side possible. If you make sure that your confidence interval are shorter than epsilon by 2, then there won't be overlap, right? So how many samples you need to make sure that it is less than epsilon by 2? That is like log t, roughly like log t because of Hofding inequality. So after log t, with the probability that there will be overlap is less than 1 by t, like roughly less than 2 by t or something, right? Because this is saying that by t is less than or equal to 1 by t, right? Like Hofding, you just equate this to 1 by t. You want with very high probability is satisfied. It means that the amount is less than epsilon. So you'll understand that n should be roughly like log t. So after you have log t samples from the first arm, like the left side arm, it won't cross that boundary with a high probability. Similarly, after having log t samples from the right side arm, it won't come to the left side. Okay. So after log t samples with a high probability, you can separate these two. So if you separate these two, according to our algorithm, which arm will we play? We play like at least one of them. It's not very good. It's not one that we will. So you play according to our algorithm. So one of them should be greater than mu minus epsilon by 2, and one of them is greater, and you'll play the arm with the highest sample average. That will have the highest sample average. So first, what you can assume is, like after log t samples from the bad arm, it will never, with a high probability, it will never after log t. So that that is best. Like unless it could have this arm, if it comes this side, what will happen? There won't be any arm which will have more than mu minus epsilon by 2. Then both will be sampled for some time because we we don't know when the right side arm will be sampled, right? Like the worst case is the left side arm is not also sampled, let's say log t times. The left side arm is not sampled less than log t, more than log t times, then we cannot guarantee this. If the left side arm is not sampled at least log t times, we cannot guarantee this, right? But if it is not sampled more than log t times, we are happy only, right? This is a bad arm. It's not sampled more than log t times, so the regret is less than log t. If you say that in the total run, the left side arm is not sampled more than log t times, that means these confidence intervals are not going to be correct, right? Because we need at least log t samples to guarantee this. So if you say that the left side arm will not be played even log t times, then I'm happy because I don't want to play the left side arm a lot of times. If the total number of times the left side arm is played is less than log t, then the regret is less than log t. Because right side arm won't contribute anything to the regret because it is the optimal arm. If the left side arm is played less than log t times, then the total regret is less than log t. That case we are happy. So if the left side arm is played more than log t times, then what can we say? We can say that the left side arm because of the Hopding inequality. Because if we have log t samples, we know that the left side arm won't cross over the boundary. Are you following what I'm saying? Or am I confusing? No, I'm saying like at a high level, I think you understood what I'm trying to give a more logical argument. So first case, let's say, let's call this new one. Let's say case one is like arm one played less than or equal to log t times in the whole experiment. If arm one is played less than log t times, what is our total regret? Because all the rounds are over and arm one has still not been played at least log t times. Then what is our total regret? It is less than or equal to epsilon log t. Because arm one, how many times you play arm one, that much regret you'll have. Epsilon into that much regret you'll have. In this case, there is nothing to worry about. Correct? So let's assume the second case is this. At some point in time, arm one played greater than log t times. At some point in time, not the total time. At some point, it will reach right. If the first case is not true, there will be some t at which you would have reached at least log t times of arm one played. Then after that, what can we say? If log t times have reached, like the confidence interval does shrink enough so that the left side arm won't cross over the two with high probability, right? So that means the left side arm uh, will will always be on the left side, like it won't come to the right side. That much we know. Let's say at that point of time, let's say the right arm has not been played enough number of times. So what can happen? Left arm has been played enough number of times, but right arm has not been played enough number of times. So what will happen? So both of us- so this is so both u bar is less u minus epsilon by 2 for both of them. So then what will we play? We'll play both arms once. That means you are improving the samples of the right arm. So at some point, what will happen? Huh? Your regret will increase because you're playing both the arms. Let's say for another log t times, you play both the arms. So the regret will become 2 log t. Okay. But in that process, you are sampling first the best arm also log t times. So after these 2 log t steps, what will happen? These two arms will get separated. So when these two arms get separated, what arm will you play? The right arm. So there won't be any more regret. So correct. So after 2 log t times, you will not have any more regret with a high probability. So the probability that you have regret is 1 by t. So it's like t into 1 by t is like 1. Right? So these are very similar to the arguments we made in all of our other proofs, like the UCB or epsilon, uh, like explore first then commit. But you have to just make the arguments properly. That's all, right? Because you see, right, at some point, if the first term itself is not played enough number of times, we are happy. There is no regret. If the first term is played, but the second term is not played enough number of times, then both will be on the left side of this boundary. So we'll play both the arms. That in that process, we are improving the samples of the right side arm. So after another log p rounds, at least both will be separated. And once both these are separated, then we'll always play the right arm if our confidence intervals are correct. If our confidence intervals are wrong, then the probability is 1 by t. The probability that our confidence intervals are wrong is 1 by t, right? The expected regret will be like 1 by t into t, which is like 1. So if your confidence intervals are wrong, there is nothing that you are going to pay. It's like expected regret when the confidence intervals is wrong is these are not very precise. I have to write down the proof if you want carefully, but this is intuitive argument that it will have a linear regret, sublinear regret. Okay. Because after log t samples from both the arms, everything looks fine. What? Yeah, this is sublinear regret, right? So the question was whether sublinear regret is possible for this or not. Order wise, it's log t is less than t, right? Order wise. Order of log t is less than order of t. How is this less than? No, we are not talking about less than root t. We are only talking about less than t, ct, less than ct. Can you speak louder? If you say log t, it is less than or equal to. Okay, so no, there is. It's a epsilon dependent constant. So it depends on the gap. So if epsilon is like it, if you say log t by epsilon, and if I tend epsilon to zero, you will get infinite. So for gap dependent bound, we have log t by delta square or something, right? Like log t by delta. That's the regret bound we have. When you don't depend on delta, then you have root t. Okay. Mhm. So, like most of the time, we just play with the Hopding inequality. Nothing else we are doing. We are just properly applying how many samples you need to say that the confidence interval is less than this with what probability. So you have to just substitute value. You have to just learn how to use that formula properly. That's the main thing. I know it's not as trivial as that, but most of the ideas are about how can we use this to say that the confidence interval is less than something with high probability. Okay. So any other thing? Question five. Question two, last part. This one, huh? Okay. So what is that hierarchy here? So what is the doubt? Huh? I think for the first round we have zero samples, right? So NT will be zero. NT minus one will be zero. So I cannot use that bound. Yeah. So I mean we have to do it for K plus something. Okay. So, I think that is just to take care of that initial condition. You can just ignore that, but that's not so important. Like, let's say, assume, let's say first K rounds if you want, or just till every arm is played once. Yeah. So, whatever that bound we have, delta, expected delta, that is applicable. What? This is like for. So, if we just don't write that and write t equal to 1 to t, what will happen? Nothing will happen. Huh? Like these things, will it create anything? Nt minus 1 of every arm is 0 at t equal to 1. At t equal to 1, nt minus 1 means n naught, right? At time 0, there is no time 0, so every arm would have been played 0 times. Yeah, that tree, not for anything. So I don't know, as I said, maybe I should count till the first time that every arm is played at least once. Or maybe I should be a little bit more careful, but that's the main reason. Just I don't want to divide by zeros. That's the only thing. No, we are not changing the algorithm. We are just saying, okay, whatever happens, I am paying at most the regret will be one. I'm not saying that I'll explore. I'm saying you do whatever you want, but I'm just using an upper bound of less than or equal to one. I'm not analyzing it carefully. I'm just saying that whatever you play, the regret at any given time slot is less than or equal to one. So I am not. Saying I'm just taking the worst case and just ignoring that part. Whatever you do, the regret in a given time slot is less than one, right? Because our delta is less than one. Hmm? Question five. Okay. No, if you allow C to depend on T, you can say C equal to T, right? Then I'm done. Right? I'll say regret is less than or equal to C and C equal to T. Like for the last question we are talking, right? C by 2 theta minus 1. So it's a universal constant. It does not depend on, like the question is at least that. Because if you say C can be a function of T, what is stopping me from taking C equal to T? The regret is less than or equal to T, right? So why should I do any analysis there? No, if it is some other, if it should not depend on T, if you want to use log T, then it's again a function of T. Right? No, like I understand log T is a better constant than T, but that's not the way to argue there. Then I could have, then they could have given it as log T by 2 theta minus 1, right, in the question. Or C log T by 2 theta minus 1, saying that C is independent of T. C log T by 2 theta minus 1. I could not still solve that question. I don't know whether there's any mistake in the question or it's just that I'm not able to solve it. I'm not sure. Because it's not a standard book. I don't have solutions for that. Because these are, as I said, these are from notes from some other lecture series. Like that questions are taken from that IIT Madras course on multi-armed band. So I don't know the answers for that, but for that particular question, I could not solve it. And that's why I just posted it on the forum so that if anyone solves it, then they can. Maybe I did not give enough bonus marks. Maybe if I had given 5 or 10 marks, maybe someone would have solved it. Any other questions? So for problem set 3, I have added some more to it. I think I uploaded only for question 1 to question 3 in problem set 3, right? So for question, given some links, you can check that. And question 7, I haven't been able to solve it yet. Question 7, I don't know the answer. And for question 5, it's trivial. Like, if you want, I can explain question. Question 2, problem. Okay. Okay. So if you remember, the arms are like this, right? So every arm has 3 parameters to learn, right? If you remember, mu a of h is like theta transpose a to h. Like h is a contest of the features of a particular user, and the true mean of arm a is like this, right? So if we had 2 features in that question, right? That's a feature vector of like 2. So it is like for every arm, like how many arms we have here? 2 or 3? 2, huh? Okay. So you have just mu a1 of x is like theta a1 x1 is theta a. What notation am I using? Theta a1 of 1. Okay. So this is 2 parameters for arm 1, and right? You have only four parameters to learn, correct? And uh, so you have whenever you play a particular arm, you get samples about the expected reward of that arm, right? You get the sample reward for that particular arm. So when you are getting one sample, right? If you want to estimate the parameters of arm A1, you just look at all the samples in which arm A1 is played. So, for example, here, this one, this one, this one, there are three samples of arm A1, right? So, what we are doing is, this is H1 and H2 in that instance. So, we'll get one equation with that particular sample, which is like theta A1 of 1 into 1 plus theta A1 2 into 3 is equal to 17. This is a sample. Okay. So now I'm just saying that like if theta A1 and theta A, like if those are the two parameters, what would have been my expected reward? This is the so we just got one equation from that. So like that you write how many ever samples you have for arm one, you just write that many equations. Then all those equations you convert it to one matrix. Similarly for arm A2, you collect all the equations, you just convert it into one another matrix. Right? So this equation will give you what? This will give you 1, 3 into theta A1, 1, theta A2, 1 equal to 17. Similarly, if you take this one, what will we get? We'll get 5, 7 equal to 2, correct? If you take this one, we'll get 11, 13 equal to 23. Okay? So that is what these matrices are. Like that is this. Right? So these are all the equations corresponding to first term. You just club them like this. So again do the same thing for the second term. You'll get the fine. Is it clear? Then the first part is fine, right? This is just a formula I just gave it so that um, the, did you guys try third part, question 3? So here we are just calculating this thing properly. That's all. And like if you recollect the policy gradient descent algorithm, we were just calculating del log phi. So we are just for this particular phi, we are just calculating the partial derivatives. Any other question? You don't know what to ask. There are doubts, but you don't know what to ask. So the exam will be open note. You can bring your notes to the exam. So no doubts on the first problem set. First problem at this time.